So, this is another beautiful problem on finding the resultant magnetic field here. See, let us read and understand. There are two identical coils carrying currents I each and have a common center. Their planes are at right angles. What is the magnitude of the resultant field at the center if the field due to one coil is B? See, he has arranged the two coils so that their planes are perpendicular to each other. See, like this. This is one coil. As you know, it will have a magnetic field produced at the center, but it will be perpendicular to the plane of the coil. So, you can say it is in this direction. Of course, he is not bothered whether it is in this direction or this direction, because he has not told you how exactly is the current flowing in that particular coil, whether clockwise or anti-clockwise, but that does not matter here. So, this is the direction of the magnetic field is what we will consider. Do not forget that the second coil that he has taken is like this, because the plane has to be perpendicular to the first one. This is the plane of the first coil, this is the plane I have taken for the second coil. So, this should have a magnetic field towards you. This will have a magnetic field like this will have a magnetic field towards you. So, there are two magnetic fields, and because the two coils are identical and also carry the same currents, the fields produced at the center of both the coils should be equal to B each. So, you are supposed to only vectorially add the two fields and get the answer. So, that would be under root of B square plus B square, which makes it B root 2. So, the correct answer there is C. Let us read the problem. When a charged particle moves perpendicular to a uniform magnetic field, its energy and momentum both change. Energy changes but momentum remains unchanged. Momentum changes but energy does not, and energy and momentum both do not change. See, he has allowed a charged particle to move at right angles to the magnetic field. That is, he has projected it with a velocity which is perpendicular to the magnetic field. And I had told you earlier that whenever you do so, the charged particle will undergo a circular motion, right? And please remember one very important point, that the work done by the magnetic field on the charged particle during circular motion is completely zero, because the magnetic field force is perpendicular to the velocity. Therefore, it cannot change the kinetic energy of the charged particle. Energy remains the same. But because it is in a circular motion, direction of the velocity continuously keeps changing, and so does the momentum. Momentum being a vector quantity, velocity changes its direction, so momentum is bound to change the direction. But energy remains constant only for the simple reason that the force which is given by your Q V cross B, according to the rules of the cross product, is always perpendicular to the velocity. Therefore, the magnetic field force does not do any work on the charged particle, and therefore, the change in the kinetic energy of the charged particle is completely zero. Therefore, let us read the options once again and try to understand which of them is correct. See, energy and momentum both do not change is a wrong option, because momentum changes there. Momentum changes but energy does not is the correct option. So, C option is perfectly correct. Okay, so let us read the problem and see what is the situation there. Two long parallel wires separated by a distance r have equal currents I in them. The field due to one exerts a force F on the other. The distance r is increased to 2r. The current in each is made to I by 2. What is the new force? So, here the first point that you are supposed to note down is they are long parallel wires. That is very important, because writing the field due to a finite wire would be difficult, or even the formula is, I think, slightly tricky. But if they are infinite wires, then take for example, there is one wire which is infinitely long and carrying a current of I, and you are writing the magnetic field due to it at a distance of r. It will be mu naught I divided by 2 pi r. So, now it is this field which will exert a force on the second wire which is kept at that particular distance from the first. But of course, that should also be carrying the current. So, he has assured you that there are two wires, both of them are carrying the current of I amperes, and the force per unit length experienced by another wire, because it is in the field produced by the first, can be directly written by the formula F equal to mu naught I divided by 2 pi r into one more I, right? Because, and of course, we have taken the unit length of that particular wire to see what force does it experience. So, this is the force experienced per unit length of the second wire, which is kept in the field due to the first. Now, it is directly proportional to the current and inversely proportional to the distance, you can notice here. So, he has said the current has been made half. So, numerator has been reduced and denominator has been increased. So, naturally the force should be reduced, right. So, no question of saying that the force will become 4F or remains F. So, those two options are straight away ruled out. The only two options left will be C and D, and let us try to put the values and verify which of them is correct. So, the new force F1 will be mu naught. Instead of I have written I by 2 whole square and then divided by 2 pi. Instead of R I have made 2R. So, that makes F1 as mu naught I square divided by 16 pi R. See, this is 4, 8 and 16. So, 16 pi R. Out of this, mu naught I square divided by 2 pi R was F. So, this will be F divided by 8. So, F by 8 is the right option there. Therefore, the correct answer is okay. So, let us read the problem and try to see what exactly is the situation. There is a magnetic needle which is kept in a non-uniform magnetic field. It experiences a force as well as a torque, a force but no torque, a torque but no force, neither a force nor a torque. See, let me remind you here, if you keep a magnetic needle in a magnetic field, it is no doubt going to experience a force, because magnetic needle will have, as you know, a north pole as well as a south pole. North pole would experience the force due to the field in the direction of the field, south pole would experience the force opposite to the field. So, you can say if the field is uniform, the net force would be 0, because it is on the same needle that you have two forces which are equal as well as opposite. Remember, the field is uniform. Now, had you aligned the needle exactly in the direction of the field or opposite to the field, then these two forces would be in one line and they would get cancelled and would not constitute any torque also. Therefore, if the field were to be uniform and the needle were to be aligned in the direction of the field or opposite to it, then neither it would experience any force nor it would experience any torque, right. But he has not told you how it has been kept, and moreover he has also told you that the field is not uniform. Then the force experienced by one of the poles, say north pole, would be different from the force experienced by the south pole, and moreover, as the alignment is not clear, it is quite possible that the needle may also experience a torque. So, the right option here would be that it would experience a torque as well as a force. That is, the first option is perfectly correct. See, I think I must have told you earlier that whenever there is a current carrying conductor, say of length L, carrying a current of I amperes, placed in a magnetic field, already existing magnetic field, say B, then the force it would experience would be I dl cross B. I is the current, L is the length of the conductor, and B would be the existing magnetic field, I dl cross B. And again, by the rules of the cross product, this force will be perpendicular to both dl also as well as B also. Let us read the problem and see how does this connect with the given situation. A straight conductor, horizontal conductor of length 0.5 meters and mass 50 grams is suspended by two vertical wires. A current of 5 amperes is set up in the rod. What magnetic field should be set up perpendicular to the rod in order that the tension in the supporting wires would be 0? Right. So, he wants here the weight of the rod to be supported by the force that the rod would experience due to the magnetic field. If a magnetic field is set up and if that wire is carrying a current, if the rod is carrying a current, then certainly it would experience a force due to the magnetic field, and if that can take care of the weight of the rod, I think the rod can be certainly in equilibrium and the tension in the two wires supporting the rod would be 0. So, let me write down the force in the rod due to the magnetic field. But please remember, I am assuming that the current in the rod is like this. The current in the rod is from the left of the board towards the right, and I have taken the magnetic field to be into the board perpendicular to the board, which makes the force acting on the rod due to the magnetic field to be I dl cross B in the upward direction. So, I L B should be equal to M into G, and that makes B equal to mg divided by IL. Now, if you substitute the values, you get B equal to M is given to be 50 grams, remember. So, it would be 50 into 10 to the power of minus 3, G would be 10. So, this would be mg divided by I is given to be 5 amperes and L is given to be 0.5 amperes. Now, if you simplify this, it would be 0.5. So, 0.5 gets cancelled and you get only 1 by 5, which is nothing but 0.2 Tesla, and that makes B option perfectly correct.